Exercise 1919 is asking you, for each compound below, identify which position or positions is or are most likely to undergo an electrophilic aromatic substitution reaction. And so these, first you're replacing a hydrogen with a certain branch. So you're putting a branch on benzene. Benzene is aromatic. And you're doing that by tempting benzene with a really strong electrophile. So these are electrophilic aromatic substitution reactions. They're the type of reactions like bromination or sulfonation or nitration or the Friedel-Crafts reactions that we drew mechanisms for earlier in the chapter. So if you want to put an electrophile onto these benzene rings, where will it add? And what they give you are benzene rings that already have a bunch of branches on them. So the first step here, and also we'll do this just for practice, is to identify whether each of these branches is an activator or deactivator, strong, moderate, or weak, and then also whether each one is ortho-para-directing or meta-directing. And once we have each of those identified, I'll talk about how you can use that information to think about where your new branch that you're trying to add to this benzene ring, where that branch will attach, whether on this carbon, or this carbon. Okay, so the first step is just to look at the branches and identify what type of activators or deactivators they are and what type of directing effects they have. Now, going from the left to the right, NO2 is one of the strong deactivators. And so this is going to be a strong deactivator. And strong deactivators are all meta-directing. Okay, going next, we have an alkyl group. Alkyl groups are weak activators. Remember, alkyl groups are any hydrocarbons. So we have a weak activator. And all activators are ortho-para-directing. And then on the right here, we have a nitro group again. Nitro group is one of the strong deactivators, one of those 3 strong deactivators that you want to know. So that's a strong deactivator. And all strong deactivators are meta-directors. So that will be a meta-director. Okay, when you have more than one branch on a benzene ring, the one whose directing effects determine where the branch goes is the most activating branch. So we have 3 types of branches here. We have a strong deactivator, we have a weak activator, and we have a strong deactivator. The most activating of those 3 things is the weak activator. You could think of it as being the highest up on this table. A weak activator is higher up than a strong deactivator. And so we're going to use the directing effects of that thing. So we're not going to consider the directing effects of the weaker activators. We're only going to consider the directing effect of the most activating thing. So if we try to add a new branch onto this benzene ring, it's going to add ortho or para to this methyl group. So this right here, this is your methyl group. The ortho positions are already taken. The only place where the new branch would add would be at the para position. So here it says, for each compound, identify which positions are most likely to undergo aromatic substitution. It would be all the positions drawn, but of course, since there are already branches on the ortho positions, your new branch would only go onto the para position. So for example, if you treated this molecule with nitric acid and sulfuric acid, then you would get the NO2 group that you would add. That NO2 group would be added at the very bottom And this molecule is actually TNT. So notice the ortho positions were already taken, so it adds to the para position. Yeah, but this molecule is TNT. TNT stands for trinitrotoluene. And so here we have 3 nitro groups. And if you remember, a methyl group on a benzene ring is toluene. So trinitrotoluene, that's TNT. Okay, so that's what you would get, for example, if you did a nitration on that ring. So the branch would add there. Okay, let's follow that same process for B. So here, first step, just to get some practice, is to identify all of these as activators and deactivators and what type, and also as different types of directors, ortho-para-directors and meta-directors. So the first thing we have on the left here is a nitro group, and remember a nitro group is one of the 3 strong deactivators that you want to be familiar with. So that's a strong deactivator. And all strong deactivators are meta-directing. So that's going to be meta-directing. Similarly, the nitro group over here is also one of those 3 strong deactivators. So that's another strong deactivator. And all strong deactivators are meta-directing. Finally, up here we have an alkyl group, right? Any hydrocarbon is an alkyl group, and so alkyl groups are weak activators. So this is a weak activator. And all activators are ortho-para directing. So that's going to be ortho-para directing. Okay, so once you have each of those laid out, the directing effects that are going to dominate will be the directing effects of the most activated thing. So the thing that is highest up in this table. And that is the thing that's a weak activator. The weak activator is more activating than strong deactivators. So where will the new branch add? It will add ortho and para to this methyl group. Now notice, one of the ortho positions is taken, the para position is taken, but this other ortho position is open. Now the new branch can't add where there's already a branch, and so it will only add here. So the new branch, whatever recipe you use to put a branch on there, that branch will add at that carbon. So we can go through that same process for C. So we're going to go one branch at a time. Let's think about this branch on the left. You know, this oxygen has 2 lone pairs there. If oxygen doesn't have a charge and it has 2 bonds, then it has 2 lone pairs. You can always think about how many atoms it needs around it in order to have an octet. 2, 4, 6, 8. Excuse me. So what we have here is we have benzylic lone pairs. We have a lone pair on the benzylic position. And that is allylic to these pi bonds, so it's going to push electrons into the ring through resonance. At the same time, though, it's allylic to a pi bond away from the ring. So if you have a lone pair on the benzylic position, but resonance is pulling it away from the ring, then that is a moderate activator. So this is a moderate activator. And all moderate activators, all activators in general, are ortho-para directors. So this is an ortho para director. Okay, next branch, we have this here. That's an alkyl group, it's a methyl group, and methyl groups or alkyl groups, those are weak activators. So this is going to be a weak activator. All activators are ortho-para directors. So this is an ortho-para director, and that is that branch. And then finally, on the right here, we have a pi bond to an electronegative atom. That's on the benzylic position. It's conjugated with the ring, so that's going to use resonance to pull electrons out of the ring. That is a moderate deactivator, a pi bond to an electronegative atom that's conjugated with the ring. And so that is a moderate deactivator. And all moderate deactivators are meta-directors. So that's going to be a meta-director. So we have our three things here. The directing effect that wins is always the directing effect of the most activating group. So the group that's highest up in this table. So highest up in that table, and the moderate activator is the highest compared to the weak activator and the moderate deactivator. The moderate activator is the highest, and so it's the moderate activator that is going to win and decide the directing effect. So I'm going to erase those other two just so I don't get confused. This moderate activator is what's going to win. It's ortho-para directing. So the ortho position on one side is taken, the ortho position on the other side is open, and the para position is open. And here, let me actually use orange for that just to be consistent. So one ortho position is taken, the other ortho position is open, and the para position is taken. Well, you can't add a branch where there's already a branch, and so the new branch would add at that one open ortho position. Okay, let's go through that same thought process for D. Now, one thing to note here is that this CN, that's actually carbon triple bonded to nitrogen. Okay, so let's think about these branches one at a time. First, we have an alkyl group. It's a methyl group. Alkyl groups are weak activators. So that's going to be a weak activator. And all activators are ortho-para directors. So that's that. On the other, in the middle, we have the CN. Now this, in this cyanide, in the CN, notice you have that pi bond there. You have a couple pi bonds there. But you have a pi bond to an electronegative atom, a pi bond to the nitrogen on the benzylic position. That pi bond is conjugated, because it's there, you have a pi bond there, single, double. The pi bond is conjugated with the ring, and so that's the definition for a moderate deactivator. Pi bond to an electronegative atom conjugated with the ring. And so that is going to be a moderate deactivator. And all moderate deactivators are meta-directing. Okay. And finally, on the right side, we have another alkyl group. We said alkyl groups are weak activators. And so that is a weak activator. And all weak activators, all activators, are orthoparadirecting. Okay, so we have these different branches with their different influences, and the directing effect that wins is the directing effect of the most activating group, the group that's highest up on this table. And those are the weak activators. So this moderate deactivator, that will not influence the new branch that you're adding onto this ring. These other two branches tie, though. And so notice, for this one, so we could possibly get a mixture of products. Let's think about what we could get. For this branch, the one ortho position is taken, the other ortho position is open, and the para position is open. For the other branch, one ortho position is taken, the other ortho position is open, and the para position is open. So you can't get the branches where there's already a branch. And so we're left with those two positions. So you could write two products, but the truth is those are just one product. There's a line of symmetry in this molecule, and those two positions are really the same. So if you add something to this ring, that new branch would add to either one of those positions and give you the same molecule, either one you add them to. Okay, let's go through that thought process for E. So for E. Now, let's draw in the lone pairs so that our eyes don't play tricks on us. This nitrogen needs a lone pair there in order to have an octet. It doesn't have a formal charge, so we don't have to worry about extra lone pairs. And then this oxygen has a couple other lone pairs there. Okay, well, on the left, this benzylic position has a lone pair. We have a lone pair on the benzylic position that's allylic to these pi bonds, and so it can use that position to push the electrons into the benzene ring. However, it's also allylic to this other pi bond going away from the ring, and so those electrons don't just go entirely into the ring. So that's the definition for a moderate activator. Lone pair on the benzylic positions, but it's involved in resonance going away from the ring. So that's a moderate activator. And all activators are orthoparadirecting. So that'll be ortho-para-directing. If we look at the branch at the top, that's an alkyl group. All alkyl groups are weak activators. Remember, alkyl groups are hydrocarbon chains. We have a CH3 there. So that's an alkyl group, and it's a weak activator. Oops. And all activators are orthoparadirectors. And then finally, this third branch, we have a pi bond to an electronegative atom on the benzylic position. That pi bond is conjugated, double, single, double, with the ring. So that, a pi bond to an electronegative atom conjugated with the ring, if you have that pi bond to the electronegative atom on the benzylic position, that is a moderate deactivator. And all moderate deactivators are metadirectors. Okay, so we have these three branches, each with their directing effects, and the one whose directing effect wins is the one that's most activating, and here that's the moderate activator. That's highest up on this. It's higher than the moderate deactivator and the weak activator. So I'm going to erase the directing effects for these other, less activating groups, and it'll just be the effect of the moderate activator that wins the day here. So it's ortho-para-directing on one of the, so this is, we're looking at this branch here, one of the ortho positions is taken, the other ortho position is open, and the para position is open. And so in this example, you're going to get two products. The branch, whatever new branch you're trying to introduce, it will add to the left in one product, and this is a different position on the right. There isn't symmetry in this molecule, so these are both different positions that whatever branch you're adding will also add at the other position, the para position, in another product. And so you'll get more than one product when you try to do an electrophilic substitution reaction with that molecule. Okay, let's go through the same process here with F. So we have this halogen at the left, halogen at the left, and halogens are weak deactivators. Weak deactivators, though, the halogens are ortho-para-directing. They're the deactivators that are ortho-para-directing. The next groups, both of these two groups, are alkyl groups. They're hydrocarbon chains, and so they're weak activators. Both of those are weak activators. All weak activators are ortho-para-directing. And then the OH on the right, that alcohol, notice that that oxygen has two lone pairs there in order to get a full octet. And so because there are lone pairs, that's a benzylic position. Because there are lone pairs there, that is an activator. And notice that the lone pairs, they're allylic to these pi bonds, so they're going to be able to push themselves into the ring, make the ring a better nucleophile, so they're activating, and they're not being pulled away through resonance at all. So if you have a lone pair on the benzylic position and no resonance pulling it away from the ring, that's a strong activator. So this here will be a strong activator. And all activators are ortho-para directing. Okay, well, the directing effects that win, so each of these branches has its own directing effects. The directing effects that the branch that wins, whose directing effect wins, is the most activating one. And here, that's the strong activator. That's the one that's highest up on this table. So I'm going to erase the information for the other ones. And we'll just think about the directing effects of this strong activator, our most activating group. So we're looking at ortho and para to that OH. Well, one of the ortho positions is taken. The other ortho position is open, and the para position is taken. So a new branch can't add where there's already a branch. There's only one place left. Whatever you add to this, whatever recipe you use, that new branch will have to add at that position. Okay, so now let's look at this ring, this for G. And for G, we have a few different branches. First, we have two alkyl branches. Those are both weak activators. And all activators all activators are ortho-para-directors. So this is going to be ortho-para-directing. In the middle, we have a halogen. The halogens are weak deactivators. The halogens, though, in addition to being weak deactivators, are ortho-para-directing. Okay, well, if we're trying to add a branch to this ring, we want to know where it's going to add. We look for the directing effects of the most activating branch. And those are the weak activators. The weak activators are highest up here. They're higher up than the weak deactivators. So they're the most activating thing, and so we can get rid of that, and we just have to consider these alkyl groups. Now these tie, so we have to think about the directing effects of both of them. So first let's think about this one. You could get a branch at the ortho positions to that. One of the ortho positions is taken, the other ortho position is open. Or you could get a branch at the para position. Okay, next, let's think about the other alkyl group. You could get a branch at the ortho positions for that. One is taken, one is open, or the para position for that. Now you can't get this branch on the bromine, there's already a branch there, and notice that there is symmetry in this molecule, so both of these two positions are actually the same. So you could put the new branch at either of those positions, and it would really be the same molecule. Okay, let's try H. So with H, we'll go through each of these branches. Notice this oxygen here has a lone pair. It has two lone pairs. Notice this methoxy group has a lone pair there. And so, first, we have a lone pair on the benzylic position, and it's not being pulled away through resonance, so that is a strong activator. And all activators are ortho-para directing. For the next group, the methoxy group, notice you have lone pairs on that benzylic position, and they're not being pulled away from the ring through resonance, so that is another strong activator. And all activators are ortho-para directing. For our third branch, it's an alkyl group. This is a hydrocarbon chain, and alkyl groups, any hydrocarbons, are weak activators. So that's going to be a weak activator. And all activators are ortho-para directing. Finally, we have a halogen. Halogens are weak deactivators. And the halogens are also ortho-para directing. So these are our branches and their directing effects. They may all be competing. The one that wins is the strongest activator. the most activating thing, the thing that's highest up in this table, and those are the strong activators here. So I'm going to get rid of the weak activator and the weak deactivator. The most activating things are the alcohol and the methoxy group. So let's think about these one at a time. This alcohol is a strong activator and it's ortho-para-directing. So one of the ortho positions is taken, the other ortho position is open, and then the para position is taken. Okay, so those you can't get a new branch at, but we could get one at the ortho position here. For the methoxy group, both of the ortho positions are taken, but the para position is open. And so you will get a mixture of products. You will get the branch, and these are different positions. There's no symmetry in this molecule. So the branch will add to the left in one product, and then you'll get a second product where whatever branch you're adding to the ring would add to the carbon on the right. So you'll get two products with whatever reaction whatever branch you're putting on here, you'll end up getting two products, one at each of the open carbons. Finally, we have I. And this is, it looks like it's 3 rings. You can definitely frame it that way. But you can also think of this as one benzene ring with 4 different branches. 1, 2, 3, and 4 branches coming off of it. So let's think about it that way. In this first one, we have a pi bond to an electronegative atom that's conjugated with the ring. And that is the definition for a moderate deactivator. So this is going to be a moderate deactivator. Then at the bottom, what we have is an sp3 hybridized carbon. This is really a carbon chain, so that's an alkyl group. And the alkyl groups are weak activators. So that's a weak activator. Oops, let me just fill in the directing effects here. For that last one we did, that moderate deactivator, the moderate deactivators are all meta-directing. And the weak activators, oops, they're all ortho-para-directing. And notice that the branches on the other side are exactly the same. Here we have that pi bond to an electronegative atom that is conjugated with the ring. And really the molecule is symmetrical. On the bottom, we have the same alkyl group. So this top one is a moderate deactivator. It's the same branch on the left as on the right. And it's also all moderate deactivators are meta-directing. And at the bottom, this is also a weak activator. And all weak activators are ortho-para-directing. So when we're trying to think of how a new branch would be directed, where a new branch would be directed, we look at the most activating group. And so these deactivators won't be the influencing factor, it's the weak activators that will be. Those are the highest thing here. Weak activators are above moderate deactivators. So the position of this new group that we're trying to add are going to be determined by these weak activators. They tie, and so we could potentially get a mixture of products. Let's think. Well, here, that's what we're considering. We could get the position ortho, that's taken, the other ortho position is open, and the para position is taken. So you can't have branches add where there's already a branch. For the other alkyl group, it adds ortho-para. One ortho position is taken, another one's open, and the pair of positions taken. You can't add a branch where there's already a branch, and so there's only one position that's available. Whatever addition reaction you try to do, bromination, nitration, sulfonation, Friedel-Crafts alkylation, the new branch will only add on that bottom carbon. So this is a first step to predicting products and to coming up with our own syntheses, is to figure out where our new branches are going to be adding on these benzene rings with many branches, on these poly-substituted benzene rings.